Bismillahirrahmanirrahim. Assalamu alaikum students. This is our lecture number 4 of X-ray diffraction techniques for MS Chemistry semester 2nd. In this lecture, inshallah, we will discuss about the crystallization, precipitation and types of crystallization. First of all, we are going to explain the crystallization. Crystallization is the natural or artificial process of formation of solid crystals precipitating from a solution, melt, or more rarely deposited directly from a gas. Crystallization is also a chemical solid-liquid separation technique in which mass transfer of a solute from the liquid solution to a pure solid crystalline phase occurs. The low nucleation rate and high growth rate gives big crystals. If the nucleation process is high, the high nucleation rate and low growth rate gives very small crystals or precipitates, depends on conditions, temperature, solvents, pH, pressure, etc. Crystallization is actually a process with respect of precipitation. Actually, the precipitation is obtained through a variation of solubility conditions of the solute in the solvent as compared to the precipitation due to chemical reaction. In the crystallization, when a substance is dissolved in a specific solvent or in the liquid melt or with something else, then it can be precipitated by varying the factors, just like by cooling temperature, by evaporating the solvent, by changing the pH or by changing the pressure. What is nucleation? The nucleation is the step where the solute molecules dispersed in the solvent start to gather into the cluster. Simple, it is the deposition of the particles of substance present in the solvent. Precipitation. Precipitation is the formation of a solid in a solution or inside another solid during a chemical reaction or by diffusion in a solid. The liquid remaining above the solid is in either case called supernatant or supernatant. Here is shown by the cuvettes. In test tube, from the left side it is the solution, and in the center it is suspension, and at the end or at right side, when the particles of solute becomes precipitated and they are settled down due to greater density, the solution or which is above the precipitate is known as supernatant. Steps in crystallization process. The crystallization process consists of two major events nucleation and crystal growth. First of all, we are going to discuss the nucleation. Actually, the nucleation is important stage of the precipitation process. It is the onset of nucleation. Nucleation is the step where the solute molecules dispersed in the solvent start to gather into cluster on the nanometer scale, elevating solute concentration in a small region. Because when the solute molecules are gathering at a specific point, at that point which is on a nanoscale, it becomes more concentrated, because at that point molecules of this actually solutes are concentrating. That becomes stable under the current operating conditions, temperature or supersaturation, etc. The creation of a hypothetical solid particle includes the formation of an interface, which requires some energy based on the relative surface energy of the solid and the solution. If this energy is not available and no suitable nucleation surface is available, supersaturation occurs. Crystal structure. Crystal structure is a special term that refers to the relative arrangement of the atoms, although those are a result of the internal structure of the crystal. At the stage of nucleation, the atoms arrange in a defined and periodic manner that defines the crystal structure. Note that crystal structure is a special term. In mineralogy and crystallography, crystal structure is a unique arrangement of atoms or molecules in a crystalline liquid or solid. A crystal structure is composed of a pattern, a set of atoms arranged in a particular way, and a little exhibiting long range, order and symmetry. It is the step where the solute molecules dispersed in the solvent start to gather into clusters on the nanometer scale. Elevating solute concentration is in a small region is nanometer scale. That becomes stable under the current operation condition. Next one is crystal growth. The crystal growth is the subsequent growth of the nuclei that succeed in achieving the critical cluster size. Nucleation and growth continue to occur simultaneously while the supersaturation exists. Actually, supersaturation is the driving force of the crystallization. Hence, the rate of the nucleation and growth is driven by the existing supersaturation in the solution. Factors that affect the crystallization: first of all, role of temperature and saturation. However, when the clusters are not stable, they redissolve. For that purpose, the clusters need to reach a critical size in order to become stable nuclei. In actual, the clusters are crystals formed in the process. They need to become the stable nuclei. If the clusters are not stable, they become dissolved in the solution again. Such critical size is dictated by the operating conditions, maybe temperature or supersaturation, etc. These are the artificial methods to prepare the crystals. For crystallization or recrystallization to occur from a solution, it must be supersaturated. It means that the solution has to contain more solute entities, means molecules or ions that are dissolved than it would contain under the equilibrium saturated solution. For that purpose, these can be achieved by various methods, with the solution cooling, addition of a second solvent to reduce the solubility of the solute. This technique is known as anti-solvent or drawn out. Chemical reaction, change in pH being the most common methods used in industrial practice. Other methods such as solvent evaporation can also be used. Lower nucleation rate and high growth rate gives big crystals. High nucleation rate and low growth rate gives very small crystals or precipitates. Depends on conditions, temperature, solvent, pH or pressure. This is the process which is showing the preparation of nanoparticles either by fast or slow nucleation. From the left side, these are precursors, and when the fast nucleation occurs at the end, you can see the arrow which is showing the growth. At the end, these generate small nanoparticles, and by slow nucleation, because for slow nucleation or slow crystallization process, it is the time taking process, and when we provide a large time for the particles to arrange, they will easily arrange in their well-defined pattern and ultimately generate large nanoparticles. This is single solvent crystallization. Typically, the mixture of a compound A and impurity B are dissolved in the smallest amount of hot solvent to fully dissolve the mixture, thus making a saturated solution. We can say that first of all, we have to prepare the hot saturated solution for crystallization. When hot saturated solution is prepared, then the solution should be allowed to cool. As the solution cools, the solubility of compounds in solution drops, because at low temperature the solubility of a substance decreases. As we will drop or low the temperature, then the solubility will also be decreased and the soluble amount of solute will be crystallized. This results in the desired compound dropping or crystallization from the solution. The slower the rate of cooling, the bigger the size of crystals, as we have discussed in the slow or fast nucleation process. This is the process. In the beaker 1, the solvent is added. As the solvent is pure, then it will be clear, and when a compound is added, it gives orange color. And the beaker 2 is heated. The solvent heated to give saturated compound solution, which will become orange. The saturated compound solution, which is orange, allowed to cool over time to give the crystals, and orange colored crystals, and a saturated solution which becomes pale orange. Repeated recrystallization results in some loss of material because of the non-zero solubility of compound A. It means the compound A is not zero soluble. Mean some of the amount will also be dissolved in the solvent. The crystallization process requires an initiation step, such as the addition of a seed crystal. In the laboratory, a minuscule or smaller fragment of glass, which is the glass piece, produced by scratching the side of the glass recrystallization vessel, may provide the nucleus on which crystals may grow. It means for the crystallization process, there must be a nucleus or a substance or solid particle at which the smaller solute particles present in a hot saturated solution start to grow or deposit. Successful recrystallization depends on finding the right solvent. This is usually a combination of prediction or experience and trial or error. The compounds must be more soluble at the higher temperature than at the lower temperature for this purpose, because we will prepare hot saturated solution at high temperature, and in hot saturated solution there is a large amount of solute. When that solution is allowed to cool, then at lower temperature a large amount of solute becomes insoluble and they are precipitated. Multi-solvent recrystallization. In the multi-solvent recrystallization, we use more than one solvent. The two solvents which are used are more than two solvents. There are two possibilities which will be discussed here. This relies on both compound A and impurity B being soluble in a first solvent. The method is the same as the above, but where two or more solvents are used. The second solvent is slowly added. Either compound A or impurity B will be insoluble in this solvent and precipitate, while the other of compound A, impurity B, will remain in solution. Heating is not required for this technique, but can be used. This is the process shown by the multi-solvent step. From the left side, the solvent is added, which is clear and orange compound. Solvent heated to give the saturated compound of the solution, which is orange in color. And here the second solvent, which is blue in color, is added to compound and the solution becomes Green, because we have already the orange in color, and when in orange blue color is added, the resultant color will be the green. And mixed solvent system, green allowed to cool over time to give crystals. Orange and a saturated mixed solvent system, green blue, will be obtained. The reverse in this method can be used where a mixture of solvent dissolves both A and B. One of the solvents is then removed by distillation or by an applied vacuum. In this, the first solvent added clear to compound orange, then solvent heated to give the saturated compound solution which is orange in color, and then second solvent which is blue in color is added to compound solution orange to give the first mixed solvent system which is green. And then the volatile first solvent which is clear is removed by evaporation. From first mixed solvent system green to give a second mixed solvent system dark green. Second mixed solvent system which is dark green allowed to cool over time to give crystals which are orange in color, and a saturated second mixed solvent system which is blue green is obtained. Hot filtration recrystallization. For the hot recrystallization, hot filtration can be used to separate compound A from both impurity B and some insoluble matter C. This technique normally uses a single solvent system as described above. When both compound A and impurity B are dissolved in the minimum amount of hot solvent, the solution is filtered to remove insoluble matter C. This matter may be anything from a third impurity compound to fragments of the broken glass. For a successful procedure, one must ensure that the filtration apparatus is hot in order to stop the dissolved compounds crystallizing from solution during filtration, thus forming crystals on the filter paper or funnel. One way to achieve this is to heat a conical flask containing a small amount of clean solvent on a hot plate. A filter funnel is rested on the mouth, and hot solvent vapors keep the stem warm. Jacketed filter funnel may also be used. The filter paper is preferably flatted rather than folded into a quarter. Often, it is simpler to do the filtration and recrystallization as two independent and separate steps. This is dissolve compound A and compound B, which is impurity, in a suitable solvent at room temperature. Then they are filtered to remove insoluble compound or glass, to remove the solvent, and then recrystallize using any of the methods listed above. This is also the process. First of all, we take the clear solvent and add the orange compound, and then it is heated and we get purple color. In purple colored insoluble substance is added and in the hot saturated solution, and we get the orange colored substance, and the insoluble substance which is purple. The saturated compound solution orange. Filter to remove insoluble substance purple. Saturated substance compound solution is allowed to cool and we can get pale orange colored substance. Seeding. Seeding is the important part of the crystallization step. We have discussed that the crystallization requires an initiation step, and that step is called seeding. In the seeding, it can be spontaneous or can be done by adding a small amount of the pure compound, which is called a seed crystal, to the saturated solution, or can be done by simply scratching the glass surface to create a seeding surface for crystal growth. It is thought that even dust particle can also be used as simple seeds, single perfect crystals for X-ray analysis. Keep in mind that growing crystals for X-ray crystallography can be quite difficult. For X-ray analysis, single perfect crystals are required. Typically, a small amount, 5 to 10 milligram of pure compound, is used for the technique, and crystals are allowed to grow very slowly. Several techniques can be used to grow these perfect crystals. Slow evaporation of a single solvent. Typically, the compound is dissolved in a suitable solvent and the solvent is allowed to slowly evaporate. Once the solution is saturated, crystals can be formed. This is the process. Again, we are explaining. First of all, we take the solvent, which is clear in color and compound. When it is added, it will become the orange in color and solution will be orange. Vessel sealed, but a small hole allows solvent vapors which are clear in color, means they are colorless, to slowly evaporate from compound solution, which is orange, over time to give crystals orange, and a saturated solution pale orange will be obtained at the end. Slow evaporation of a multi-solvent. As same as above, however, as the solvent composition changes due to the evaporation of the more volatile solvent. The compound is more soluble in the solvent, which is volatile, and so the compound becomes increasingly insoluble in solution and crystallizes. This is the process, which is again shown. We have clear solvent and orange compound, we will get orange colored solution. And second, blue solvent, when added in the orange, it will become green. Again, sealed the vessel and a small hole is present on the lid, allows solvent vapors which is volatile and it is evaporated, and a saturated mixed solvent which is blue-green is obtained. Thank you.